Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. Previously, we added directional lights to Primal engine and we used them to light all objects in the scene. However, in the real world, most lights come from sources that are relatively close to objects they affect. The most common way of modeling this kind of lights in computer graphics is by using point lights, also known as omnidirectional lights, and spotlights. Today we are going to expand the light module to support these light types as well. Before we work on lighting code, I'd like to quickly show you how we can improve our camera movement code using input binding events. Because although we wrote these functions to handle binding events, we didn't actually get to use them. Right now we are polling for a binding value during the update every frame. A more efficient way of doing this would be to ask the input system to notify us whenever the binding value was changed. Therefore, we can attach an event handler for the move input binding. This function is called whenever there is an input from any source that contributes to this binding. The onMove event handler should have the same signature as the binding callback type defined in input system class. So it receives the binding key and a reference to binding's input value. Now, instead of calculating a move vector in the update function, we are going to add it as a member variable. We are also going to add its length in order to quickly check if it's non-zero. A non-zero length would mean that the move vector has non-zero components, and therefore we need to move the camera. In the event handler, we simply set these two new member variables. Note that I'm calculating the square of the vector length, which will save us one square root calculation. In the update function, we can remove all of this and then just check if we have got a non-zero move magnitude. In that case, we use the move vector to move the camera. The rest of this code can remain the same, except we now pass the frame time to camera stick function because we removed the frame time member variable. We can move around, but now we are using the input events instead of polling. I'll do a couple of small improvements next. Here we can use this reference instead of looking up the binding again. And here, where we remove a source from an input binding, we can just remove it right away instead of using its index later on to remove it. I also made a typo here, which I need to fix. Next, I forgot to add this key, which is called a tilde, to our enumeration for input codes. We need to also map it in the platform-specific part of input system. Next, I would like to provide the option for mapping a specific input source axis to any binding axis. And finally, we need to pass a proper array of thresholds to our frame info. We also assert that we have at least the same number of threshold values as the number of render items. Okay, great. Everything still works and we can move on to writing the lighting code. We already have point lights and spotlights in light type enumeration. I'd like to start with adding the accessor functions for the additional properties that these lights have. The first one is the attenuation, or the rate of fall off, which doesn't apply to directional lights, but it does to all other light types. We can pass up to 3 floating point values to parameterize the fall off function. There are a variety of ways to model this, and I'm not sure yet which one we'll end up using. Next one is the range. This is where the light's intensity approaches 0 after applying the fall off function. We can use this range to cut lights from parts of the scene that are out of range. The cone of a spotlight can be described using 2 angles. The umbra is the cone where the light's intensity doesn't depend on the angle with the light's direction vector. The penumbra is the cone where the light's intensity gets weaker the more we deviate from the light's direction vector. Both umbra and penumbra must be greater than 0 and less than 180 degrees. In addition, the angle of umbra can never be greater than penumbra. These are all the setters and getters for our new light types. Before implementing these functions, let's add the data containers and write the code that will add, remove, and modify the light data. Internally, we have the concept of the light owner, which has an ID that points to the actual light data. We did this in order to be able to tightly pack the light data. This wasn't necessary for directional lights, because the number of those lights is low in general, and if someone would try a large number of directional lights, they would be bottlenecked by the pixel shader much sooner than by memory latency. However, the number of point lights and spotlights can get quite large, and that's why we want to be as efficient with handling light data as we can, and therefore we are going to use tightly packed arrays for point lights and spotlights. I'll explain how this tight packing works in a bit, but first we need to define the light parameters data structure, which will be used both in the shader code and in C++ code. So I'm going to add it here in commontypes.hlsli. Here we put all parameters that we need to calculate lighting for both point lights and spotlights. In the future, we might want to use more compact buffers by splitting the light parameter buffer into multiple buffers for each light type, but for now let's go with this data structure that applies to both light types. Note that we passed the pre-calculated cosine of the half angles of umbra and penumbra for spotlights. While we are here, let me define the data structure that's used for light culling. Light culling is the subject of the next episode, but I can already reveal which properties we are going to use. For spotlights, we need the cone radius at the bottom of the cone, which we use to do cone plane intersection testing. Again, we'll see how that works in the next episode. Back in the light set class, we add an array of light parameters and an array of light culling info. To make it easier to get entity transforms, we also put the entity IDs for each cullable light in an array. We can also quickly look up the light's owner using an array of light IDs. When we change any of the light properties, including the position and direction, then we need to update this data in the GPU buffers as well. That's what this dirty bits array is for. The elements in this array have a bit set for each frame buffer that needs to be updated with light data. Now let me explain a bit about how we pack the data in these arrays. When we implemented directional lights, we added a free list which we called light owners with its elements pointing to the light data. We separated the light data that we sent to the GPU from other data, such as light's entity IDs, to make it easier and faster to update GPU buffers. There is also another reason that's got to do with how we manage cullable light data. Because the number of point lights and spotlights can become rather large, it's extremely beneficial to put only the data which is used by the GPU to do lighting calculations in an array, and to keep that array as compact as we can. In addition, because light culling stage uses a different set of light data than the shading stage, we have split the data for each one into a separate array. We also have an array of IDs which point back to light owners. Later we'll have a few more arrays, but I'll use these three for simplicity. The explanation remains the same when we add more arrays. When handling the data, we can view each element in these arrays as being part of one item that is split between the arrays. For example, when we remove a light, we need to remove it from the same entry in all arrays. As I mentioned, light owners point to their data using an index, and the data point back to an entry in light owners array. I duplicated this free list in order to avoid having arrows all over the place, but it's the same free list displayed twice. Now the idea is that we keep all light data for lights that are enabled in a contiguous array. We have a counter that keeps track of how many lights are enabled. For example, if we want to disable the second light in this list, we swap its data with the last enabled light. We also update the indices in light owners array to point to the new locations. And finally, we decrement the enabled lights counter. Now we are left with a tight array again. We can do the same trick when we want to remove a light. However, this time we remove the light owner and also mark the owner ID with an invalid ID. Again, we decrement the enabled lights counter. As a last example, when we enable a light, we can swap it with the first disabled light and increment the counter. When we want to add a new light, we start by looking for an empty slot after the enabled lights. We keep track of how many lights are currently enabled using this member variable. Note that this only applies to cullable lights. We are not including directional lights in this count. As I mentioned earlier, we mark a removed light by setting its owner ID to invalid. If we couldn't find an empty slot, then we need to add a new entry to all arrays of light data. We also assert that all cullable light arrays have the same size. Now we have an index where we can put the data. It doesn't matter whether it came from an empty slot or a new entry in the array. We call a couple of functions that will write light parameters and the culling data to their respective entry in the arrays. Next, we create an owner for the light data and add it to its free list. Then we set the entity ID and the owner ID of the light, as well as its dirty bits. I'll define the dirty bits mask in a minute, but let's finish writing this function first. We continue by enabling or disabling the light depending on the initialization info and update the light position and direction by calling yet another function that we need to write. Finally, we return the light with the owner ID and the light set key. Now I'll define the dirty bits mask, which is just a U32 integer with as many bits set as there are frame buffers. And speaking of being dirty, let's use some of that revolting C++ metaprogramming, because every now and then I just like to feel absolutely filthy. So here we have a template class that takes a number between 1 and 32 in its template argument, and set the bit with a position that corresponds to n-1. It then logically ORs the value that's acquired by recursively declaring the same class for n-1. Next, we add a specialization for this class for when n equals 0, in which case the value of bits is 0. This specialization stops the recursion and we end up with as many bits set to 1 as the number n. You can see that for the current frame buffer count, which is 3, the first 3 bits are set, resulting in a value of 7. If the frame buffer count is 2, we end up with 2 bits set to 1, and so on. Also note that the static assertion will fail when the frame buffer count is too large. Now we can initialize our dirty bits mask constant with this value, which will confuse Visual Studio beyond repair. Having done this and making sure that everything still compiles when we exclude the function calls to the non-existent functions, I'll call it a day on this one and go sit in a corner to ruminate on what I just did. Not to worry, of course, for we shall continue this in the next video. As always, thank you so much for joining me today, and I hope to see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus, there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!